In this video, we'll take a look at the Gated Recurrent Unit, GRU, a recurrent neural network model that simplifies the complex structure of LSTM while still delivering strong performance. If you haven't already, I recommend watching the previously uploaded videos on RNN and LSTM first. They'll help you understand this one more easily. First, let's take a look at RNN and LSTM. Vanilla RNN has the advantage of a simple structure, but as the sequence gets longer, it runs into the long-term dependency problem caused by gradient vanishing and exploding. As a result, earlier information gradually fades over time. To address this issue, LSTM was proposed. By introducing 3 gates and a cell state, LSTM successfully alleviated the long-term dependency problem. However, this more complex structure increased the number of parameters and computational cost, which can slow down training. Because of this, researchers started looking for a more efficient architecture that could balance the simplicity of RNN with the strong performance of LSTM. That's how the GRU was introduced. As you can see on the screen, GRU is a recurrent neural network model that simplifies the structure of LSTM. Unlike LSTM, which uses 3 gates and a separate cell state, GRU consists of only 2 gates, the reset gate and the update gate, and a single hidden state. One key difference is that unlike LSTM, GRU does not have a separate cell state. In other words, it removes the cell state and keeps the architecture more compact. That's the main feature of GRU. Now let's take a look at the reset gate. The reset gate determines how much of the previous hidden state is reflected in the candidate hidden state. If you look at the equation, we multiply the current input x sub t and the previous hidden state h sub t minus 1 by their respective weights, and then pass the result through a sigmoid function. The value of r sub t falls between 0 and 1. If it's close to 0, the past information is largely engored. On the other hand, if r sub t is close to 1, the previous hidden state is largely preserved, meaning the past information is largely preserved. So basically, the reset gate decides how much of the past information should be reset. Next, let's talk about the update gate. The update gate basically combines the roles of the forget gate and the input gate in LSTM into a single mechanism. In other words, it determines the interpolation ratio between the previous hidden state and the candidate hidden state, thereby controlling how much the hidden state is updated. If you look at the equation, we take the current input and the previous hidden state, apply their respective weights, add them together, and then pass the result through a sigmoid function. Next, let's look at the candidate hidden state. The candidate hidden state is a new proposed state that's computed by combining the current input with the previous hidden state, which has been adjusted by the reset gate. If you look at the equation, we first apply the reset gate, r sub t, to the previous hidden state, h sub t minus 1, using element-wise multiplication. This step determines how much of the past information will be reflected. Then we take this adjusted hidden state and the current input x sub t, apply their respective weights, add them together, and pass the result through a tanh function to compute the candidate hidden state. Finally, let's talk about the hidden state. Unlike LSTM, GRU does not use a separate cell state. Instead, It manages all the information using just a single hidden state. The final hidden state is computed as a weighted sum of the previous hidden state, h sub t minus 1, and the candidate hidden state. If you look at the equation, the previous state is multiplied by 1 minus z sub t, and the candidate hidden state is multiplied by z sub t. We subtract z sub t from 1 so that the two weights add up to 1. Here, 1 minus z sub t represents how much of the past information we retain, and z sub t represents how much of the new information we update. In other words, the update gate z sub t controls the balance between past and new information. If z sub t is close to 0, most of the past information is preserved. On the other hand, if z sub t is close to 1, the previous information is mostly discarded, and the new candidate hidden state becomes the main source of information. Here, let's take a look at why we don't simply use the candidate hidden state as the final hidden state, and instead incorporate the update gate. If we directly use the candidate hidden state as the final hidden state, the model would essentially behave like a basic RNN. In that case, the gradient would pass through multiple multiplicative steps over time, making it more vulnerable to the gradient vanishing problem. However, by introducing the update gate, we combine the previous hidden state and the candidate hidden state through a weighted sum. This creates an additive path for the gradient, rather than a purely multiplicative one. Because of this additive structure, the gradient can flow more smoothly across time steps, which helps alleviate the gradient vanishing problem. Finally, let's compare LSTM and GRU from a structural perspective. First, if we look at the number of gates, LSTM uses 3 gates: the input gate, forget gate, and output gate. In contrast, GRU uses only 2 gates: the reset gate and the update gate. Also, LSTM manages information using both a cell state and a hidden state. On the other hand, GRU doesn't have a separate cell state and relies on just a single hidden state. Because of this, LSTM generally has more parameters, requires more computation, and has a more complex structure. In comparison, GRU has a simpler architecture with fewer parameters, which reduces computational cost and often leads to faster training.